Bismillah. Hello. This video will explain the shape function in finite element analysis or finite element method. I am Asif from Mechanical Design Engineering at National University. This is actually an assignment of the advanced numerical analysis supervised by Professor Sijo Kim. So in this video I will discuss about shape memory functions properties, the formulas, requirements, and examples. So this is actually the introduction of shape function. Well, um, before going to finite element analysis, some continuous models are approximated using some information at a finite number of discrete location. That means we need to discretize the model into piece by piece, and we need to converge it uh, after discretization. So for that reason we need to identify the points, and we need to make some meshes or shapes, and from that shape we need to collect the data from that. So the interpolation within that elements is achieved actually through shape functions. So basically the shape function is a function which interprets the value between the discrete mesh nodes. So lower order polynomials actually are chosen as shape functions. So the function is a displacement function as well as the interpolation function. So yeah, in this video we will discuss about the properties of shape function. First of all, what is shape function? It's a function, I have stated it before, that interpolates or explains the solution between the discrete values obtained at the mesh nodes. We need to create the mesh nodes here, and it will interpolate the solution between the discrete values. So the properties of shape functions belongs to the Kronecker. I will discuss the Kronecker delta property briefly, Lagrangian shape functions, and serendipity shape function. Also, in this video I will discuss the requirements, that is interpolation, locus support, continuity, completeness, and compatibility. And also there are some classifications in the element form, polynomial degrees, and types of shape functions. And at the in the end of the video, two 3D example will be discussed and how can we solve that. So the basic concepts are the discretization concept. Say for example there are some continuous solution field such as stress, that could be stress, displacement, temperature, pressure, etc. Here is you can see the temperature rise with the distance. Well, it's a one-dimensional temperature distribution. First of all, what we need to do is we have to discrete this model and in a piecewise continuous function, and that will make some finite number of subdomains. So here you can see if we discrete this model into piecewise continuous function, then it will separate it in various parts, and this is the approximate piecewise linear solution, and we can integrate that and we can get the um, area. And if we can discrete it as much we can, we will get the exact value, or we will get near to the exact value. So there are a lot of way or a lot of approximation for discretization. Say for example, here I have mentioned the linear interpolation of model where there are four elements, 1 2 3 4. So and another one is quadratic interpolation model. And quadratic interpolation model, there would be a point that is in the middle point, and yeah, so in the piecewise linear approximation, actually the temperature, here you can see the temperature, this temperature is continuous. Okay, so in the A figure you can see that the temperature continuous, but the discontinuous temperature gradients, but in the B it's clear that the gradients are continuous. However, we'll go to the some approximations. The approximations would be the yeah, we will get to the polynomials first. Polynomials are constructed for approximation functions for each element, actually. So for each element we need some of the polynomials that is dependent on the order of the approximation, different numbers of the element parameters, something like that. And there are some special approximation that depends on the special properties determined by the theoretical consideration. So you can say this is a basic orientation. You can see that this is linear, quadratic. In the quadratic, some of the points will be in the middle, and yeah, and in the cubic, yeah, actually it represents the order of the polynomials, and if it's cubic, yeah, the figure is quite like that. So however, we will skip this ones first. So for the requirements, actually for shape functions requirement, it needs to be converged first. So the mesh that is refined in finite element analysis solution, that should approach to a analytical solution in the mathematical model, and it should be converged after all of that. So for this conversion, there are some requirements such as interpolation. So what is interpolation? Actually it needs it takes unit value at node, say for example in this node, it takes a unit value, and for other nodes it is 0. So other nodes is 0, but it needs a unit value here. And for local support, actually in local supports it doesn't include the node, but it vanishes over element boundary. It is located in a side of a if there is a 2D structures, something like that. So it depends situated in the side and of 2D, and if it's 3D, something like that. If it's 3D, then it locates on the faces on a 3D surface. Okay. So the increments of compatibility, this actually requires the continuity between the adjacent elements over any element boundary that includes nodes. And the requirement of completeness, the interpolation has to represent something. What is that? It should represent the rigid body displacement and the constant strain rate. So yeah, if these two are considered together, then we can tell that the case that we have considered is consistent. And last of all, the compatibility, which is very important. This interpolation is such that the field of displacement should be continual and derivable inside the elements. and also continual across the element border. Okay, for this is the description for compatibility. Well, you can see here the discretization of a shape, and if it's loaded axially, then the shape will be stressed along this axis, but it provides the displacement continuity. Yeah, it provides the displacement continuity here. Yeah, if you provide this load in this axis, then all these nodes seems like continuous and provides displacement between the elements, something like that, and ensures no material gap. There shouldn't be say for example the nodes here and the nodes here shouldn't be something like that, and other peer nodes should be like that. This shouldn't be happened. Okay, so it ensures the no gap rather than compatibility. And the shape functions must be the continuous between the elements and piecewise differentiable. So this is for the deformed shape, and I have showed it for the continuous load along the axis. So next, get to the completeness. So this completeness actually, say for example, this is a cantilever beam, whether cantilever beam can be extended, pressed down, or rotated. And if it's pressed down, then this shape will be deformed like this, and this is actually the rigid body transition, rigid body rotation, and deformation would be like this. So how this can be represent, what this represents? This represents the rigid body displacement with a constant strain rate. There must be some constant strain rate, and it must represent exactly all polynomial terms of order which is less than m in the Cartesian coordinates. Okay, so a set of shape functions that satisfies all conditions is called actually m complete. So yeah, we can see that a set of shape functions, if we select this area, these nodes, for defining the completeness, it could be said at m complete. And there are some classifications. The classification depends on the element, that could be triangular, rectangular, or others, and polynomial degree of shape functions, that would be linear, quadratic, cubic, and something like that. We will discuss it later. And the shape functions, the Lagrangian serendipity, these functions. So what is Kronecker delta property? This is very important, because Kronecker delta property, the shape functions at any node has a value of 1, just 1, and just at the node all the value would be 1 and a value of 0 for all other nodes. So yeah, we will get the example later, and it also detects illustrates that the compatibility and completeness make the convergence, and it ensures to get better as more elements are introduced in the limit approaches to exact answer. So it helps to get the exact answer and define one node's value which is 1 and other node's value which is 0. That is a good approximation for solving the problems. Going to Lagrangian shape functions, this is the actually basic um, equation for Lagrangian shape function, and this is the short term for polynomial of order m at node k. Okay, so these are the facile example here. You can see that if the conditions is quite like that, then yeah, if this is the origin point, then if we want to detect the node 1, then it would be half of 1 minus z, because it is going to the negative portion, and for the positive portion it would be half 1 plus z. And for quadratic example, this would be n1, which is going to, yeah, since that it is going to the minus area, the negative area, so this zeta would be minus, so you can see that minus half of zeta into zeta and 1 minus zeta. How about the 3? Then this portion is the positive portion, so this would be half of zeta, 1 plus zeta. And how about the middle one? This is important, which will be applicable in the next examples. So here at the point, so this will be what can I say, interpreted as 1 minus zeta and 1 plus 1 plus z, 1 plus z and 1 minus z. That could be written as 1 minus z square. How about the cubic one? There are a little trick for the cubic one, because for the cubic one there are 4 parts, 1 2 3 4, so this would be 4 square, see that, 4 square. And for n1, if you got here, then it would be 3. For 2 it is 27, that is 3 cube, and this is 3 cube, and this is 3 square. Okay, so how it is depicted like this, we will explain it later. So yeah, there is another example that there are 6 points here, and this is z naught, this is minus 1, minus 7.75, and actually this function's function is equal to 1, and whole function is equal to 0. How about, let's skip this one. For Lagrangian family in the Pascal scale, we can get the one-dimensional equation for node. This is a polynomials for one-dimensional equation. This is the lower order triangles, and yeah, actually this is the quadratic linear equation, and this is the higher order polynomials. So we can take it at p0, which defines nothing, and if we go for p1, that is 1 2 3 4, and that has 4 points, 4 nodes here. And for p2 here, you can see that for p2 this is 1 2 3 4 5, so 6 7 8 9. So for p2 you will get 9 points, and for p3 you can count the nodes depicted from the Pascal scale depending and the Lagrangian relating to the Lagrangian family. So if the order n element has how many nodes there are, if we just tell the element number n, the element number n can be get easily by n plus 1 whole square. If the if the n is equal to 1, you can see that if the n is equal to 1, then the nodes will be n plus 1, that is 4. If n is equal to 2, then it will be 9. N is equal to 3, that would be 16. So we don't have to rely on the Pascal scale again and again for solving the equations or problems. We just need to remember this one. So yeah, how the local local coordinations are created. Well, if the local coordinations x-axis point is z1 and z2, that can be depicted x minus xe, where xe is the center of the global coordinate and ae and be are the dimensions of the element. So for 4 node bilinear, I will show the 4 node, this one 4 node, 9 node and 6 nodes bilinear quadrilateral equations. So how about this one? The equations of node 1 is quite like that, depending on the shape functions equation that I have described in the previous slide, and obviously depending on the local coordinates. So what about this one? This is n1, which is 1 by 4, and if we consider it 0, then the 1 is located here, so it will go minus to the x point, x-axis, and minus to the y-axis. So it would be 1 by 4, 1 minus z1 for x-axis, 1 minus z2 for y-axis. What about the this one? This would go 1 by 4, yep, and for x1 it will go for 1 plus z1, and it will go to the minus negative 1, so 1 minus z2, yep. So for n3, how about n3? It will go 1 by 4, 1 plus z1 and 1 plus z2, yes, that it is. And for node 4, it would be 1 by 4, 1 minus z1 and 1 plus z2, yeah. So by following this, we can get the node the shape function equation for 4 node bilinear quadrilateral. So yeah, there are some types of examples. This is bilinear, you can see that. For bilinear, this is 1 2 3 4, and the biquadratic. What is biquadratic? If it is quadratic, then there would be a division of the total mesh. If it's bi, so it would be divided into 2 portions. In one portions, there would be a rectangle, this one. This is biquadratic. How about bicubic? If it's cubic, then there would be 3 boxes. Yeah, since it's bicubic, then it is 1 and 2. And what about the quadratic linear? The quadratic, in the previous slides we have seen that the quadratic linear is 1 point is the one end, 1 point is the another end, and 1 will be the middle. So for this rectangle, this would be, if the quadratic linear is defined, then it will be like that. And for linear cubic, it will actually it follows like this. Since it's linear, so there wouldn't be any points into this rectangle. And how about the linear cubic? It is quite similar to this one. See that? But yeah, it will just follow these lines. How about the quadratic cubic? For the quadratic cubic, that means there will be quadratic 2 boxes here, and since it's cubic, so 1, 2, there will be assured. For cubic, there will be 3 boxes, and for quadratic there will be 2 portions, 1, 2. And what about the quadratic? Yeah, that would be fun, because for quadratic it will be divided into 2 portions, and these 2 portions, 1, 2, 1, 2, yeah, something like that. So yeah, for quadratic we can gauge the total nodes. Also we can assume the total nodes also. Let's wrap this up. Okay, let's go to next slide. So for 9 node biquadratic quadrilateral, the equations for the for the shape functions for this corner 1, 2, 3, 4, the general equations is quite like that. Actually, yeah, 1 plus z I1, that is the coordinates of the of this point. Z I1, this is the x-axis coordinates, and that means we have defined it before that in the local coordinates this x-axis will be regarded as z1, and this y-axis will be defined as z2. So these coordinates has come from the z1 axis. How about this one? This comes from the z2, the value of z2 axis. Yeah, we can also simply think that this is x and this is y for the local coordinates. However, for these middle points of the lines, the equations are like that. And for 9 here, so this is 1 minus zeta square and 1 minus zeta z1 square and z2 square. Well, we will figure out just one point here. How about the n1? If this is n1, we will relate this one with this equation. So for n1, this is -1 and -1. We will plug in this value in this equation. So this would be -1. So there will be minus. This would be -1. So there will be minus. this will be -1, there will be minus, and this will be -1. So this minus is outside of the bracket, so this will be, this 2 will be plus, so there would be just z1, this will be plus, so and z2. So here you can see here z2 and z1. What about this one? There was a minus, so 1 minus zeta z2, 1 minus z2, here it is 1 minus z2, and this one 1 minus z1, and 1 by 4. Okay, similarly for these points, for 0.5, we will just plug in the coordinates of the 0.5, plug in the points of the this node 5, and we will get this equation, and from this equation the visualization will be like that, and we will get this equation for the 9. For 16 node by quadrilateral, the equations is like that. You just need to plug in the coordinates, and we'll get these results. This is for the 1, and this equation for the corner, the node in the corner. These equations are for these points, and this equation is for the the points located here, and these equations is for the nodes that is placed in the rectangle. So serendipity elements, okay, sorry for the pronunciation, and these serendipity quadrilateral elements, the bilinear, biquadratic, bicubic, is almost similar to the previous one, but there is no nodes into the in the rectangle. So how we can get that? Let's find it out with the Pascal scale. It comes from, this is P0, it has we will not consider that. It comes from like this, so there are 4 nodes, 1 2 3 4. Okay, so for P1 there will be 4.1 2 3 4. And what about the P2? The P2 will be regarded like this. How about how many points, how many nodes? 1 2 3, 1 2 3 4 5 6 7 8. So here for P2 we will get 8 points. How about P3? 8 9 10 11 12. So here we will comes 12 points. So relating to this Pascal scale, we can get the node of the meshes. Okay, so rectangle boundary nodes that is expressed by the Serendipity family. This is the linear, quadratic, cubic, and quadric. For quadric there is a node. It should be kept in mind. Well, we are getting to the end almost. So in the serendipity elements, the equations are expressed like this, where the functions ni, z1, z2 are the Lagrangian interpolations, and these are the corresponding boundary and values that have 0 or 1 value. So here is an example that will ease our understanding. So you can see that there are half 1 minus z2 ni. this is 1 minus z2, and the equation the um, coordination of the point of certain node, this is 1 plus z1. This is for the z1 axis, this is for the z2 axis, and you can see the corresponding uh, equations or corresponding terms for each axis, and these terms are different, so there are literally two sections. So we will detect the n3 here. So how about n3? If we place here n3, then we have to keep in mind that these nodes points are here 1, 0. So we will just plug in here. If we plug in here, we can see that for 0 we can eliminate the terms for z2 here and this one. I'm sorry. Yep. So since the z1 value is positive, so we can eliminate the negative values here, this one. So we will eliminate this term, we will eliminate this term, and we will accept these two terms, and that will be half 1 plus z1, and this will be n3, and 1 comma z2. What about this one? Half 1 plus z2 and n3, z1 comma 1. And we will, since this is in the first coordinate, so we will eliminate this coordinate. This is minus 1, that is fourth coordinate. This is not the first coordinate, and this is the third coordinate, so we will just accept this one. So this term, this term, and this term. After that, after some interpolation, we can get this answer. Okay, next, the triangular elements. So for triangular elements, the coordinates will be zeta1, zeta2, and zeta3. It will be converted into shape functions, and we will get the geometry and the displacement. So if these two nodes are fixed and this can be shifted, then this node 1 is its original position, and this is the different position. So we can get the deformation by detecting the displacement of this node. And what is A here is actually the area, and A1, A2, and A3 are these particular areas. So for defining the nodes, it's easy, because it's just n1 by a1 by a. Total, you have to divide by the total area to the particular area, and you will get the n1. This is n2 and n3. So think about the Kronecker formulas that has the total according to that shape function, this will be regarded as 1. The total summation of the nodes is 1. So if the n1 is z, n2 is eta, n3 is will be 1 minus zeta minus eta, and they are the 6 nodes of triangle and with their function plots. Well, here we have come to the example for the tetrahedron element, and this is in the global coordinates, and this is actually the simplest 3D element having 4 triangular faces. This has 4 nodes and 3 degree of freedom x, y and z. So if we define it in a local coordinates, that is z, eta and zeta, that would be quite like x, y, z. And yeah, this is the shape functions equations, and I have built a local coordinates here for one section. So you can see that this is node 1, 2, 3, 4. So for node 1, from the Kronecker formula of properties, the node 1, it has only one value, that is 1, and other value is 0. So if we just plug in the coordinates respect to this node, then we will get like this. So this is 1, node 1, and if we plug in this one, then the a naught plus z will be 1 here. If we plug in here, z will be 1 and others are 0. This is 0, so the equation will be a naught plus a1. And for this one, this is totally 0. However, this one, think about it, the node is 0, other node's value is 0, so this will be 0. And if we just plug in the coordinates number here, the coordinates number is 0, 1, 0, so it will be 0, it will be 1, and it will be 0 for this point. Okay, so we will get a naught and a2 from point 2, so a naught and a2, and similarly we will get this one. So summarizing these equations, we can get a naught, a2, a3 is equal to 0 and a1 is equal to 1. And yeah, so we can say that the n1, so yeah, n1 is equal to z, and if we have to erase this one, if n1 is defined as z, n2 is eta and n3 would be zeta, so the n4 will be 1 minus z minus eta minus zeta. However, the hexahedral element, this problem has been inserted from one of the YouTube video of Indian professor, and yeah, here is a linear hexahedral element which has these coordinates. So for master cube Lagrange function, the equation is quite like that, which is yeah, where the I is equal to 1 to 8. There are 8 nodes. For 8 nodes, we will just plug in the coordinates into these equations. What about it? I will just demonstrate one for n1, how it has come from. Yep, this one. So in the zi, eta I and zeta I, we will just input, we will just plug in this value. So the zi is -1, eta I is -1, and zeta I is -1. So we can get the n1 in this function, like this equation. And similarly to this procedure, we can get this 8 nodes of a hexahedral elements. Okay, so here is the end of the video. So we have learned about the shape function properties, some example, and how it can be applicable in the finite element analysis, how we can detect the points and the point properties and the node equations we may have defined this one. Thank you.